Beneath the concrete floors of modern data centers, our global communication relies on thousands of miles of physical, vulnerable glass fiber optic cables. Right now, hostile state actors are actively tapping these lines. They copy petabytes of encrypted financial records, military communications, and infrastructure blueprints, stockpiling them in data silos under a strategy known as Harvest Now, Decrypt Later. The encryption protecting that data is secure today, but the timeline for its expiration is approaching. Quantum computers scale up physical qubits to actively run algorithms like Shor's, which factor the prime numbers securing classical cryptographic systems in polynomial time. The massive vaults holding our digital history are secure only as long as quantum computers remain in the laboratory. To counter this threat, engineers proposed a solution built on the absolute laws of physics, quantum key distribution. Cryptographic keys are encoded into physical single photons. The no-cloning theorem dictates that copying an unknown quantum state without disturbing it is physically impossible. If an eavesdropper measures the photon in transit, the observation collapses the wave function. The data is destroyed, instantly detecting interference. Theoretical physicists constructed a shield mathematically proven to be information theoretically secure. Humanity believed it had engineered a protocol completely immune to computing power. But mathematical proofs assume perfect execution. They do not account for the classical thermodynamics of copper wires, optical glass, and physical hardware tolerances. In 2011, a quantum hacking group led by Vadim Makarov set out to test the physical endpoints of these systems. Their goal was to execute a perfect eavesdropper attack against a commercial quantum network. Using a rugged suitcase filled with standard optical components over a 290-meter fiber link, Makarov's team intercepted a secure quantum key. They triggered 0 alarms and left no trace in the quantum bit error rate. The laws of quantum mechanics held up perfectly. The physical hardware built to read those mechanics failed completely. The exploit did not occur in the fiber optics. It occurred at the destination, inside the receiver hardware. The protocol bottlenecks at a single photon avalanche diode, visualized as a spring-loaded trap. Operating in Geiger mode, bias voltage pushes it to the breakdown threshold. A single photon strikes, springing the trap and initiating a current avalanche to register a click. The integrity of a multi-million-dollar network relies entirely on this microscopic physical trap remaining precisely calibrated. Makarov's team bypassed the quantum mechanics by targeting the detector with classical light. They directed a weak continuous wave laser directly down the fiber line. This continuous beam strikes the diode, creating a steady flow of photocurrent across the resistor. The delicate trap is flooded with continuous energy. Because of that steady current, the bias voltage plummets well below the breakdown threshold. The detector is forced out of Geiger mode and into classical linear mode. In this state, it is blind to individual quantum photons. With the receiver blinded, the hacker intercepts the quantum states. They measure them, copy the data, and send brief, bright flashes of classical light to the receiver, manually forcing the hardware to click exactly when they want it to. Simple physical heat and stray capacitance overwrite the mathematical model. The receiver registers a perfect key exchange, completely unaware it is communicating with an eavesdropper. Beyond hardware exploits, physical quantum networks face massive architectural bottlenecks. The systems require direct, point-to-point physical fiber connections. They cannot scale across modern routers, network switches, or wireless infrastructure. To compensate, the protocol encounters the Authentication Paradox. Measuring a photon guarantees no one intercepted it in transit, but it cannot verify the identity of the person who originally sent it. To prevent a man-in-the-middle attack, a quantum network must authenticate the sender's identity using classical, math-based algorithms. The protocol relies on the exact mathematical systems it was designed to replace. Despite these physical vulnerabilities, the Chinese government invests heavily in continental quantum key distribution, deploying thousands of miles of dedicated point-to-point fiber networks. Because quantum signals degrade rapidly over optical fiber, these long-distance connections require physical trusted relay stations to bridge the gaps. At every relay node, the key must be decrypted into classical data and re-encrypted. This introduces physical security vulnerabilities and insider threats at every stop along the line. In contrast, the United States National Security Agency explicitly rejects quantum key distribution for national security systems. Intelligence agencies recognize the friction of hardware dependence. Geographic limitations and fragile equipment introduce more risks than they mitigate. Instead, the NSA and international security bodies recommend post-quantum cryptography. This approach uses advanced lattice-based mathematics to resist quantum computer attacks, requiring no specialized physics hardware. It is scalable software. It deploys instantly across the existing global internet infrastructure, securing data over standard commercial routing protocols. While quantum computers threaten older algorithms, cryptographers have already engineered layered mathematical structures capable of withstanding those future machines. In securing the infrastructure of the future, flexible software running on standard hardware proves more resilient than a rigid theory isolated in a laboratory.